Sure.
And what we'll do is as normal. I think Andre's going to do the first half, and Bryn will do the sort of standard side chat for questions there, and maybe Carl-Henrik and I will also chip in, and then they're going to switch around. So off you go, guys. Thank you.
Okay. Is my screen coming? All right. Perfect.
Yep, we can see it.
All right. Thank you. So, welcome everyone. My name is Andre, and together with Bryn, we're going to talk about our work for Delve and for one of the reports, which Neil just beautifully introduced. So I hope we don't need to talk about COVID-19 here. I hope everyone is familiar with what COVID actually is. If it was a major change in pretty much everyone's life these days. If for some reason you are not familiar with that, then I just tell you welcome back to Earth. It's nice to have you here, and the next couple of days you will learn a lot of amazing news. 2020 was a blast. So back to COVID. Back when it hit, that was obvious that you need to do something to. It's a disease and it's potentially deadly, and you need to do something to stop it from spreading, or at least control it, right? And in the ideal world, we would have a vaccine for it, but unfortunately, as you probably aware, vaccine stays years to develop properly. There is a lot of testing that they're potentially dangerous. There might be side effects, so we can't have a vaccine like tomorrow. It will probably take still some time, even though the efforts on it are great at the moment. It will take time before vaccines are developed. So in the meantime, we should do something else. And this something else is is a set of measures that businesses, governments, people on their own try to implement, to practice, to prevent the disease from spreading. They are called non-pharmaceutical interventions, or NPIs, and you will hear us refer to it, NPIs, farther down the talk. So NPIs could be wearing masks is an NPI, or practicing social distancing, or maybe when it comes to government, enforcement some kind of a lockdown. So something we're currently experiencing right now, right? All of these are examples of measures that you could try with various degrees of effectiveness to implement, so that you stop ideally, hopefully, but realistically just slow down COVID from spreading, as well as other diseases. And today focus is on testing, tracing, and isolation, which is just one of these NPIs, right? So let's talk about this in a little bit more detail. What is it? So test means you obviously do tests for people who have symptoms or don't have symptoms. So you on some ground you test people for having disease. Then once you found out the test comes back positive, you want to trace their contacts. This is what tracing stands for. So you want to understand for some amount of time going back whom these people could have contacted and therefore could have transmitted the disease to, right? And then with all of that input, knowing who has symptoms, who has COVID, and who they were talking to or contacting, you want to isolate them. Maybe not all of these people, right? And this is one of the variables in the TTI, in any TTI policy, right? But on some, there is some decision on who should be self-isolating for some time. So TTI is widely believed to be an effective tool because it's effectively because you kind of stop people from walking around and spreading disease. Therefore, you reduce the transmission of the disease. So you make the R smaller, and R is, if you know, just the rate in which how many people a single person can infect with the disease, right? So the smaller R, the slower the disease spreads. Therefore, you have fewer cases. Therefore, you have your NHS is not as loaded, and you have more means and ways of treating the disease properly and saving lives. And that is probably our main objective right now. So TTI is believed to be a very effective tool for that, right? And as other countries have shown, it can be effective, right? So in some countries it has worked very well. But we didn't have, a certainty as to whether we can implement it effectively. But the government had. And here is a quote from Boris. It's the best quote I could find from him, which I was sure he said, right? But the general perception back in May was that TTI is going to be our ultimate weapon. The syllable that's going to just help us absolutely control the COVID. And as soon as we implement it, our lives will be pretty much back to normal. Of course, some people will get the disease and some people will have to self-isolate, but for those who don't, everything will be just fine. So that was a perception that maybe the government was kind of radiating and the public was kind of receiving. But, from scientific point of view, you should have doubts. So you should be asking yourself, is it really as efficient as everyone says it is? Right? And so how effective can it be in stopping the transmission? And if you say it is effective, so okay, what does it mean? What are the resource requirements? How do you implement it in practice? So what is the amount of tests that you would need to implement in the country of size of UK? And if you are using applications on the phones, which obviously do, how many people should install the application? Because people have doubts, and some people just miss things, and some people don't trust you to treat your data properly. So how many people do actually want to install it so that it is effective? And then for those who don't install it, you'll need to do manual tracing. Okay, how many people do you need to actually implement manual tracing? They're called traces, and they just contact people and they just talk with them and ask them, hey, hello, whom did you talk to for the past 2 weeks? So that's one aspect that you should be asking yourself. Another aspect is, what are the success factors? As in, do you know the disease well enough? Is TTI effective on its own? Do you need other NPIs? So there are many questions that you should be asking yourself before implementing such kind of policies that affects pretty much the whole country. And this is where Delve comes in. So I'm not going to talk much about it. Neil just gave a great introduction, and he described what the Delve is and what it was doing. I should probably say that it was one of the few, if not the only, cross-disciplinary group, which gave it a huge edge, because by cross-disciplinary, I mean that we had immunologists, people who, like biologists, we had specialists in weather, we had data scientists, obviously, statisticians, we had policymakers, we had active doctors on it. It's a great mix of people, so that if you look at a certain question, you can attack it from multiple angles rather than just one angle. So that was an amazing aspect of Delve, and I'm very grateful for Neil to pull me into it. And here's the website. I'm sure you can find it, and we will hopefully be able to put the slides up on the web page if you need it later, because this is not the only link we're going to be using it. Anyhow, Delve decided to answer with some of these questions. And so we published the test trace isolate report. We published this late May, just slightly ahead of the TTI actually being released in the country. It covers a lot of ground. So we've done the actual simulation, which we'll talk about later. We talked about public perception of TTI. We talked about surveillance. We talked about how important the compliance is and what we need to do to make the, encourage people to comply with the TTI policy. And we talked about practical things like the capacity constraints I was talking about earlier. So it's a very comprehensive and long read, but probably worth it. It received a lot of coverage. That much we do know. So you can see probably all the major tabloids talked about it. What we don't know for sure, because no one would share this with us, if did it actually influence the policy? Did the results of this report actually made a change in how UK officials approach TTI? We hope it did, and you can indirectly say that like the stress on other API. I shouldn't probably say that because the results will come off later, but we have some indirect indications that it probably helped form the right policy and right approach towards TTI. But TTI is still not considered to be very effective in the UK, and sorry, not our fault. Anyway, as a part of this report, Bryn, myself, and a couple of other folks in Delft created TTI Explorer. So that was a simulation that is built to explore measure and explore all the practical things, the questions that we were asking before. So it builds upon it's basically a simulation of COVID that just in fact models the population, creates some primary cases, and sees how it spreads. And depending on which TTI policy you implement, it tells you, it gives you estimates of the number of tests, traces, and the number of person days spent in quarantine, things like that. It builds upon the existing works that was released early in the year by Adam Kurczewski group. And we kind of, I like to think that we've just added a lot of practical logistical things into that model. So it follows the same concept, but it's a much more elaborate logistic workflow, how to implement a real world TTI. And it uses some BBC data for content. So this BBC data, by the way, is a very interesting thing because they basically try the life experiment of what would happen if there is a pandemic like that. But I think it happened like 4 years ago. When no one ever heard of COVID. So yeah, that's a nice thing to know that someone actually cared about epidemics long before they hit. This is what I was talking about when I said that TTI Explorer implemented like a hopefully realistic logistics of different. So what you see here is, don't try to even read these images. They're not here for reading. They just here to show the scale. So these are the flowcharts of real TTI policies that we've considered, and you can see how many steps there are. So all of these are simulated in the TTI Explorer, and you can just see that there are a lot of things to think about when you are implementing TTI policy, and there are a lot of steps to take, and it's not as trivial as probably it may seem at first. So let's talk a little bit. We won't go into many details of how TTI Explorer works. It's fully open source, but I don't think we need to really talk about the strict internals. So we'll talk about some more high level things. So first is, so imagine you have this population, And first you need to do is you need to present that there are some primary cases in this population. So single people infected with the disease, right? So here we considered three main cases. The symptomatic COVID case, the asymptomatic COVID case, and the symptomatic non-COVID case, because you can probably have a flu and it will look very similar to COVID, and you will still trigger some part of TTI. You will at least probably require a test sometime, but so you need to consider these cases in the simulation, even though they're probably not, they're not exactly relevant because it's not COVID, right? But as far as the resource requirements go, and you need to understand if you need, you need to spend a test on it, and you need to spend some time isolating person while they're waiting for the test to come back. It's still relevant, so we need to consider it. And following the work from Kucharski, we also considered context of three kinds, which you can argue, you can argue that there are more than three types, but every simulation has to make some assumption. Every simulation is kind of a incorrect representation of reality, and this is how we incorrectly represented reality. So you can have a household conduct, you can have a context at work, or if a person infected with COVID is attending school or university, then we call them school, and everyone else just falls into the other. Every other type of contact falls into the other category. Cool. So the actual simulation was considering 4 TTI strategies. First is don't have a TTI and just let it go. The other one is trace people based on their symptoms, right? So you test people based on their symptoms, but whether you trace their contacts based on their symptoms is a question. Do you want to trace on symptoms, or as the next option, test on the positive test of COVID? So they have symptoms, you don't trace anybody yet, then the result for the COVID test come back and they're positive, and then you start tracing. Or another policy that we considered is trace on positive test and also test their contacts. So you can trace the contacts and just ask them to self-isolate, or you can start testing them as soon as you find out that the primary case wasn't COVID, right? So there are 4 different approaches to how to run the TTI, and they're variable in their resource requirements and the effectiveness on stopping the R. But how effective and how different, we had no clue. So this is why the simulation exists in the first place. We pretended there are 5 different, considered there are 5 different 5 different levels of NPIs, right? It loosely follows the tier systems that the government released. So if you can say that the most strict level in our simulation corresponds to the strict account we had back in late spring, and the less strict, the least strict level is kind of no lockdown, and the others also kind of follow the government tiers, but they're not exactly that. We were not claiming that this is exactly how the tiers are modeled. So just to avoid any kind of misunderstanding here with the press. Yeah, and like I said, we were accounting for most major factors, some of which we have in here. So we were modeling people going into quarantine. We were modeling both tracing the application and manual, and we were thinking about the compliance, both in terms of going into self-isolation and installing the app, and reporting your contacts and things like that, and some other factors as well. So some results that we've obtained with it is, okay, just as we suspected, TTI alone is probably not a silver bullet. You will still need other measures in place, and in combination, then they can all together be very effective in slowing down disease, but you can't just launch a TTI and forget about wearing a mask or practicing social distancing, things like that. We found out that, kind of obviously, then self-isolating early is better than not self-isolating later, and it's very effective. So as soon as you find out that you probably have the disease, it's better to self-isolate. It's safer for others. And the absolute key success factors for TTI policy to succeed from our simulation turned out to be the time that the test takes to arrive. So I had mine once. It turned out it come back negative, but it took 2 days. So bringing that down to 1 day would be amazing. And manual trace times, especially I have manual here in parentheses, because you can also have you can also consider like application tracing, but application tracing is obviously like you would hope it's instant, right? As soon as you found out someone, and the application on the other people's phones should just tell them to self-isolate because their contact had COVID. But manual traces is all different matter, and there is a lot of discussion on the press about language barriers and such things. But actually, the time it takes to manually trace your contacts is very important. Because obviously, as the next point says, not everyone will comply with the guidance and have the application installed. An application uptake is an absolutely crucial thing. Finally, for me, some other findings that we found on the resource side, because this is one of the key questions for asking. So what is the resource requirements of TTI strategy? And like I said, manual tracing is super important, and you'll need a lot of people to do it properly, apparently. That's the only way you can make up for the low install rates of the TTI application. It turned out that, as you probably would expect, when you trace people on their symptoms, and not waiting for the test to come back, that turns out to be very expensive. You need a lot of resource to implement that properly. And finally, it turned out that if you test, so if you have a primary case and you start testing all of the contacts immediately, it has a marginal impact on R. It helps stop the disease, but not as much as you would hope. But obviously, it reduces days people need to spend in quarantine. That's it for me. For the next part, I would like to invite my peer Bryn to take over and talk to you about some other details and some ideas.
Thanks, Andre. I'm just going to share my screen. Can you see the presentation?
Yep.
Yeah, okay, cool, right. So, yeah, thanks, Andre, for doing the first half of the presentation. Thank you, everyone, for turning up and listening. It's really nice for me to be able to give a talk since I was an undergrad at Cambridge. I'm going to be talking to you about sensitivity analysis and how we used it in the TTI project. So as you've probably got from what Andre was saying, the purpose of the project was not only to analyze whether or not TTI would be effective, but to get a gauge on how effective it would be, and to understand that our metrics for how effective it is and the resource requirements of it in terms of some maybe factors of the world that we maybe understand or don't understand, and various pinch points of the strategy, for instance, important factors, operational factors, like Andre was saying, about the delay for testing and tracing and that kind of thing. So this is where the sensitivity analysis comes in. And basically, what I'm going to tell you about is the way that we use sensitivity analysis to determine the importance of various factors in TTI. Okay, so the slides move. Right, so why do we do sensitivity analysis? There's two reasons for which we used it in our TTI work. First of all, we need to know how robust our model is to the various assumptions we need to make about the world. So as you can probably tell, there's a lot of factors to do with this disease that impact the outcome in the end. So for instance, impact the rate of transmission, or impact the number of tests you need to do in a TTI system. And we're uncertain about lots of these parameters. So there's things like, as I've got on the screen, the proportion of people that are asymptomatic will have a big impact on transmission, because of course these people aren't going to know whether or not to isolate. And so we'd like to know that the results that we get from our work on which decisions might be made are robust to uncertainties in these facts of the world that maybe we're not 100% sure about. And then the second thing, as I was alluding to earlier, is identifying, as Andre called them, key success factors, or you might also call them pinch points, and figure out how important these things are. So one possible thing is the test trace delay. So this is going to be an important factor, you would imagine, for the effectiveness of the TTI strategy, because if somebody gets a test and there's a delay between their result, then they might be going around infecting people and following their normal contact patterns before they've got the result. So the result needs to be as quick as possible, and that's kind of the thing we're trying to tease out exactly that effect. Another important thing is public compliance. And when we were doing this report, there was a particular event of non-compliance that we thought was going to be important to the stuff going on in the world. Okay, so how did we do this? We chose a really simple strategies for gauging the sensitivity of our model, and I'll just talk through these now. I'm sure that the things that you've seen in the lectures are much more sophisticated, but because our model ran relatively quickly and wasn't very expensive to compute, we could just do the simplest thing. So the two strategies are these. Call the first one grid variation and the second one axis variation. So imagine we have some collection of parameters and we want to understand how some key output of the model, let's just call it the reproduction number R, for instance, or the number of tests, varies as we vary the input parameters. So just going back to the previous slide, this could be we're varying the input parameters because we think that, well, maybe the rate of proportion of asymptomatic people is between 40% or 60%, and we vary in this range to see how the output of the model changes. Or maybe we say, well, what if we could get the test delay down to 1 day rather than 2 days, and we vary in that way to get an idea of how the model responds to pinch points. So this grid variation is kind of the most naive thing you can do. You just try all the combinations of all the parameters in the collection that you wanted to check. So if you look at this chart in the bottom right hand corner, I hope you can see it. I've just done a little schematic. So you have parameter A and parameter B, and the red crosses are all the different values. Let's just say that we could check. And in the grid variation, we just check everything on this lattice. In the axis variation, however, which is the next one, this, what we're calling axis variation, is where you take one parameter at a time and move it away from its default value. So each parameter has some kind of default value that we use for the simulation in the results presented. And then one by one, we move each parameter away from its default within some bounds that we've fixed to begin with, and then and see how the model changes. So you'll notice that this grid variation is, if there's sort of m options for one and n for another, you're going to get m by n, whereas the axis variation is going to be something like m plus n minus 1, looking at that grid. So another important thing to just to bear in mind for the purposes of this work is that it's not necessarily the case that all these parameters are numerical. So you do have things such as the rate of compliance, which we modeled as each person has a Bernoulli random variable, which has this parameter P, which determines their probability of complying with a request for isolation. But there's other parameters, for instance, to do with the disease, which model the infectiousness of an infected person over time. So that could be thought of essentially as a probability distribution, roughly as the probability of a secondary contact being infected by the primary case if they meet on a certain day. So that needs to also be incorporated, and this is why this type of choosing subsets approach is relatively appropriate for our work. Okay, so I can just talk to you quickly about some results. These are some results which are in reference to the calculating how robust our model is with respect to uncertainties in various aspects of the disease that we're maybe not so sure about. So I can go through these things one by one. The chart on the left is how the reproduction number varies in various strategies that Andre outlined earlier. Those are the different colored lines. On the chart on the far left is how that varies with the day on which the primary case is most infectious. And I should say that all of these charts are for the most severe lockdown scenario. So something that's roughly what's going on now, full lockdown. If in other scenarios that we looked at, then our numbers on the y-axis are different, because obviously there's different levels of social contacts, there's more transmission. But the overall story of the charts is the same. So you can see that on the left chart, and I'll go through and explain them one by one. On the leftmost chart, the day on which the primary case is most infectious has some impact on R. And you can think that looking at this, you can decide, does our model make sense? So you say, does it make sense that TTI is more effective when the person is most infectious later in their duration of their disease? That does make sense, because it means that TTI has more time to get someone to isolate before they've infected a certain number of people. Okay. Then you can also see that roughly, if you move one day either side of the day in which they're most infectious, the R remains within the confidence interval of the day before. And that's actually true for all of these charts. Now, the central chart, I'll tell you what that means now. This is the expected number of days that before the primary case reports their symptoms. And in our model, reporting their symptoms and noticing their symptoms is the same thing. So you can think of this as, what's the expected number of days from becoming infectious until becoming symptomatic? And you see the same kind of phenomenon in the left chart, but in reverse. So it's more difficult to effectively isolate people and stop the transmission if they have noticed their symptoms later in their disease. And then one thing to remark here is that this is with the axis variation strategy. And so in each of these, you'll notice that there'll be an interplay between the left and the right chart. So if somebody is very, very infectious on the first day, but doesn't notice their symptoms until the third day, that's worse than if their most infectious day is the third day and they notice the symptoms on the third day. So these two things actually have an interplay, which is something that we're going to come up to in the extensions. The final thing is this latent period. And the latent period is the time interval between a person being infected and becoming infectious. And so what we're measuring here is to do with actually not the primary case, but the secondary case. So suppose you have a primary case that infects their friend, and this primary case gets a positive test. There's going to be some delay to do with the contact tracing system that orders the secondary case until the secondary case is ordered to isolate. Now, if it turns out that this latent period is longer, so the duration between being infected by the primary case and being infectious, so infecting other people, if that's longer, then there's a bit more slack in the system for TTI to take a little bit longer. And you could imagine that the results might be sensitive. You wouldn't want the results to be overly sensitive to uncertainty in this. So this is the ones through the uncertainty. And then the next slide I'm going to show you is something about results relating to these pinch points that we were talking about. And again, what's coming up is compliance and the test and trace delay that Andre's spoken about as well. So the different colored lines here are now the different lockdown levels. So S5 is the most severe level of MPI. That's full lockdown, staying in your house. So basically what's happening now. S1 is essentially no lockdown, but we still ask people who have symptoms to isolate. So this was what was happening right at the beginning. And then we've got various different levels in between. And in each level, there'll be different levels of social contact, and so different levels of transmission, and hence different levels of R. But the important thing to see here is, again, this is with this axis variation strategy. On the left, you have how the R varies as you vary the test trace delay at a certain level of public compliance that we assume to be 80%. And then on the right, you have how the R varies as the compliance in the community varies at a certain test trace delay, 2 days to test and 1 day for contact tracing. And what's really, really striking here is that compliance is, the test trace delay is very important, but compliance is really, really, really important. And you can also see that the if you look closely at the right-hand chart, the gradient of the blue line, so the S1 line at the top, is larger than any of the lines. Now that's because the strategy of stopping transmission in the no lockdown scenario is just asking people to isolate, and compliance determines whether or not people are going to isolate. And that's the key factor of reducing transmission. So that's why it has the largest effect in that scenario. Okay, so that's me done talking about sensitivity analysis. Now I'm going to talk to you briefly about some extensions that you could make to our work here. So there's two things I'm going to talk about in this presentation, but then in the appendix, there are more ideas that maybe when you get all of the slides you want to look through and have a think about. So the first one is, as I was talking about earlier, trying to tease out some interactions between parameters using the sensitivity analysis, and maybe using slightly more sophisticated techniques than we use. The second one, which I think is pretty cool, is can you use our model to infer some of the states of the world parameters that I was talking about earlier? So I'll just go through and explain these now. Parameter interactions, right? So when we were analyzing pinch points, like I just said, like I just showed you, we didn't really consider what would happen if some of these parameters varied at the same time in the in the second chart that I showed you. So this possible extension is basically about teasing out those relationships. And there's also other things that you could look at here, which is that we had to predefine the grid or the set of values to evaluate our parameters on. So we either defined some specific values and then iterated through them, or we gave bounds and a kind of like grid step and iterated through that. So maybe actually the way that it works in reality is that you might want to check some points very close together in one parameter space and then some further apart. So maybe there's some kind of model-based approach you could use there, or something else from your lectures to tease out those parameter interactions. Now this inference idea, right? So in the current situation, in the current simulation, we put in all these input parameters. So for instance, what is the likelihood of you, what's the probability of you infecting somebody you live with if you've got COVID? Or what is the rate of public compliance at the, that we think? We put it through we turn the crank of the simulation and out comes some number of new cases that's we're expecting, what's the rate of transmission and some other things, okay? So this idea is, can you do this in backwards? This whole thing backwards, right? Can you take real world data, real world value for R and the case numbers that we see, and then conditioned on the dynamics of the disease following our model, can you infer what the parameters such as public compliance are in the world that give these results? So that's potentially kind of a fun project that you could try. And I think, yes, the next thing is telling you about how you would do that, right? So the code, Andre and I work quite a lot on the code. So the report is at this link here. I think it's already been put in the chat. All of our code is at this link. So the TTI code is at this link within the Delve organization. Feel free to mess around with it, play with it, contribute if you spot a bug, even better. And we made an introductory notebook. If you do want to use the code, you can just go to this link in the slide. A Colab notebook will pop up, and there'll be some explanation of how the code works, and it should help you with getting to grips with the tools. So I guess we're coming to the end now. Here's the team. So I guess we've got Andrew and I both owe thanks to the rest of the team that worked on this report. That's my supervisor at EY in the top left. Myself, Michael, Bobby, and Shahaya in the bottom right are all students of EY, and Anne and Guy in the center and to the right are epidemiologists who are working on this report. And I think with that, that's the end of the talk, and I'll take any questions that you guys have.